కనిపించట్లేదు. Oxidation of alkynes. In this, first one is with Bayer's reagent. We know that Bayer's reagent is cold dilute alkaline potassium permanganate, which of course is meant for or is used for thin hydroxylation, right? Now let me give you the different cases in this. If a non-terminal alkyne is taken with the Bayer's reagent, then see at the beginning, I mean in the first step it will be hydroxylation across the multiple bond for twice. Okay. Yes. Now after this, as I said earlier also, a carbon atom having two hydroxyl groups is unstable, right? So undergoes elimination of water. Remove two water molecules and you will get a diketone. Okay. This is when a non-terminal alkyne or internal alkyne is taken. Let's see. What if a terminal alkyne is taken? Again, the same kind of thing. Add OH across the multiple bonds. Now again, elimination of water molecules. Now, in this case, we get R C double bond O, C double bond O. Here it will be just H. No much difference because it's just dilute and under hot and under cold conditions we are carrying out this reaction. The bond is not going to get broken. The same, of course, can be seen with the hot alkaline came in before. Oxidation using the hot alkaline came in before. Let us take the same alkynes with the hot alkaline MnO4. Now the bonds break because it is hot. Under hot conditions, the bonds break to form carboxylic acid, right? Then going for the terminal one. In this case, see from this end, we get a carboxylic acid. And from this end, of course, a carboxylic acid, that is formic acid. But this formic acid is further oxidized. Now, this is further oxidized to give carbon dioxide and water. Okay, that is the extra thing that happens with the hot alkaline chemical. Bonds break to form carboxylic acid. Okay. Next. Then it's, of course, ozonolysis. Within ozonolysis, we have two types, reductive as well as oxidative. First with ozone, then with either zinc water or dimethyl sulfide. See, even with the reductive ozonolysis also, we get a diketone, just as cold dilute, alkaline came in before. Now, when you go for oxidative, it will be like hot alkaline came in before reaction. Okay. Here, bond undergoes cleavage and we'll get this. And of course, RCOOH and R dash COOH, two carboxylic acids. Okay. So let us see some other reactions like the addition of HCl, hydrogen cyanide. Acetylene reacts with HCl, hydrogen cyanide, in the presence of barium cyanide. Simple mechanism. Let us take it this way. Minus here, plus here, plus here, minus here. Then it will be like minus to plus, minus. See, in this case, we get vinyl cyanide, CH2 double bond CHCl. You can say proptene nitrile, right? Or common name is vinyl cyanide, also known as acrylonitrile. It's a very good monomer. See, on polymerization, let me show you how the polymerization occurs. I've already given this in alkenes. Let me just show you how polymerization occurs. Now this is a monomer. Now just like this bond is given to form a bond with it's a succeeding molecule, a bond comes from the preceding molecule, right? Now this bond is of the molecule that we are considering, and this molecule is not of our molecule, it is a bond of its preceding molecule. Now finally, the polymer can be written as, look at this, CH2, you got a bond from the preceding molecule, then CH, then this bond which has actually gone from this area, then taken in time. So this is how the polymers are to be made. Then so this can be called polyacrylonitrile, simply given as PAN. Commercial name of this is Arlan. Arlan is a synthetic fiber. We'll come across different types of polymers in the topic polymers. Okay. So this is how a polymer is made. The monomer is vinyl cyanide and the polymer is polyvinyl cyanide, or you can say polyacrylonitrile. Right. These are all very simple. Now the addition of acetic acid. Acetylene reacts with the acetic acid. Okay. Now even this can be taken as acetate and H. Right. Now you can go this way. So we'll get CH2 double bond, then CH, O, C double bond O, CH. See, up to this, it is vinyl, right? Then we can call it vinyl acetate. Now this vinyl acetate, on further reaction with another molecule of acetic acid, we can take it the same way again. Now we get CH3, then this CH, see, this is called ethylidene acetate. Okay, a gem kind of compound, geminal. Like we say ethylidene chloride, this is ethylidene acetate. Next, addition of arsenic trichloride. Even here also, it's going to be the same. Take it this way. Let me show you what arsenic chloride is first. Can be taken as AsCl2 plus, then Cl minus. Now we have to add this Cl minus. Let me take it this way. Plus and minus, just for convenience. Now, yes, it is minus to plus, then minus to plus. They're all very simple. See, here we get Cl, CH, double bond, CH, AsCl2. So this is, of course, chlorovinyl part. Vinyl, but a hydrogen atom is replaced by a chlorine atom. So we can call it chlorovinyl. So chlorovinyl dichloroarsine. This is dichloroarsine. Arsine is in fact ASH3. Look at this. Two hydrogens have been replaced by chlorines, and this, of course, has replaced a hydrogen. So ASH3, but the three hydrogens have been replaced by different groups. So we call it chlorovinyl dichloroarsine. You know, chlorovinyl dichloroarsine is famously known as levisite. Levisite is also a poisonous gas, just like our mustard gas. Poisonous gas. You know, it is 4 times more poisonous than mustard gas. See, this mustard gas is, of course, formed when ethylene reacts with sulfur monochloride, right? Already discussed. Now, see, this levisite is poisonous. To overcome the poisonous nature of levisite, antidote is used. Antidote acts against the poisonous nature of levisite. British anti-levisite is actually used as antidote for levisite. Okay. BAL. British anti-levisite is used as antidote to levisite. Okay. Now, what is BAL? So this is British anti-levisite. When added to levisite, This is Lewisite. Lewisite, of course, is poisonous, toxic. Now, as and when BAL is added, these two hydrogens are eliminated along with the two chlorines, and it actually gets connected to Lewisite and forms a non-toxic compound. Look at this. Okay, these two get connected to arsenic, which has already got CH, double bond, CH, C. And we also have this CH2, OH, right? See, this, of course, is non-toxic, minus 2HCl. That's it. Okay. Now let us see what polymerization is. See, when three molecules of acetylene, you can also say 3 moles, no problem. Or simply when acetylene is passed through red hot copper or iron tube, it undergoes cyclic polymerization to form benzene. Okay. So this cyclic polymerization can be shown this way. Let me take the 3 molecules of acetylene in an amicable way. Right? See, it can be given as, now as and when this bond comes here, this will get negative charge, a positive. Same is the case here, negative, positive. Then again the same thing. Okay. Now just the regular practice, negative to positive. A fresh bond is formed between the two carbons, and you'll get your benzene. Check this out. See, we get C double bond C, then H, H. Here it is CH, then a double bond here, CH, CH, and this one. Yes, we have a pi bond. This is our bench. Now, if the same thing is carried out with the 4 molecules. In the presence of a coordination compound, of course, this is called tetracyanidose nickelate 2 ion. See, coordination compounds have a specific a UPAC kind of nomenclature. Okay. We'll learn about this later, of course, but for now, see, this is called tetracyanide because the carbon atom is connected to the central nickel. Cyanidose C, because there is another possibility of even nitrogen getting connected to nickel. So that is what we call tetracyanide N. Here, because carbon is connected, tetracyanidose C nickelate, nickel, and this 8 extra is because it is an anionic complex. And of course, the oxidation state of nickel here is +2. That is what is shown in Roman numerals in brackets. And it's an ion. So is known as tetracyanidose C nickelate ion. Okay. Now, in this case, we get cyclooctatetraene based on the same mechanism. Okay. You can check out the mechanism part. Cyclooctatetraene. Next. And if suppose propyne is considered, we get mesitylene in when passed through red hot copper or iron tubes. The same polymerization, but you can just replace these hydrogens by methyl. That's it. You will get mesitylene 135 trimethyl benzene or mesitylene. Okay. So with acetylene on cyclic polymerization, we get benzene as well as cyclooctatetraene, depending on the number of molecules used. And from propyne, we get mesitylene. Okay.